Hi guys, welcome back to Chapter 5, Lesson 7 here. Today we are going to be talking about probably one of the more important things that we will ever cover in Algebra 2. Today's lesson is about the fundamental theorem of algebra. Big idea here, folks. This is a super huge concept. This really hopefully will start to pull all of what we've done in linear concepts, quadratic concepts, and starts to pull it all together. All right. Now, the first thing we want to talk about is one key piece of vocabulary, and this is the idea of a repeated solution. So it says for the function f of x equals 0k f of x equals 0. K is a repeated solution if and only if the factor x minus k has a degree greater than 1 when it's factored completely. All we're saying here, guys, is remember we talked about quadratics that only had a single solution. So when they came down and they just touched the x-axis like that, those are actually, this would be a repeated solution situation. This probably factors to something like x minus 2 squared, where this factor in this quadratic has, again, this factor in the quadratic has a repeated solution here at positive 2. We can have other things, like we can have like a cubic that kind of comes in and has a flat spot right here and then kind of goes up where it has one solution. But again, it's a repeated solution. And a lot of times when our function kind of changes direction or turns kind of right on the x-axis, we get something called a repeated solution. So you can have, what we call a double root at a spot, and so you're going to be seeing some examples of that as we move throughout our lesson for today. Now, as promised, okay, we are going to first define or talk about, once again, the fundamental theorem of algebra. The theorem states very simply, it says, if f of x is a polynomial of degree n, where n is greater than 0, again it has to have a degree greater than 0, then the equation f of x equals 0 has at least one real solution in the set of complex numbers. Okay, now that by itself doesn't really make a lot of sense. We're saying every function has a solution, and it has to be at least complex. Maybe it could be real, but again, it could be complex, because all the complex numbers are numbers like a plus bi. Well, if it has a real part and without an imaginary part, then it's got a complex number solution. So that by itself is not really the exciting part. The exciting part is the corollary that goes along with it. All right? It says if f of x is a polynomial of degree n, then the equation f of x equals 0 has exactly n solutions, provided each solution repeated twice is counted as 2 solutions, each solution repeated 3 times is counted as 3, and so on and so forth. Now, this is a fantastically huge idea. I can't stress this enough. What we're saying that is some function, for example, y equals x squared plus 2x minus 7. This is a second degree polynomial, and so we know that this has 2 solutions. Now, do both of those solutions have to be real? Not necessarily, but it has 2 solutions. All right? And again, we're going to be taking a look at how we come up with those solutions here shortly, but at least understand that the number of solutions will be dictated by the degree of the polynomial. All right, so it says find the number of solutions or zeros of each of the equations or functions. It says because x to the third, again, it's third degree, it is a third degree polynomial, so it has 3 solutions. Now, you can look at that function, and maybe that function, we talked a little bit about cubics and then behavior and all that kind of stuff in section 5.2. Maybe it looks something like this, all right? Maybe it looks something like this, all right? In this case, it has 1 real solution, and so the other 2 must be imaginary. In something like this, maybe all 3 solutions are real, all right? In letter B, it says because f of x is equal to x to the 4th, this is a 4th degree polynomial, and so it has 4 zeros. Now, is it possible that this is a 4th degree polynomial and has a shape sort of like this, where it has no real solutions? Sure. Well, that just means that all 4 of its zeros are all imaginary. Okay. Could it have 2 real solutions and then 2 imaginary and look something like that? Absolutely. It could have 2 reals and then maybe 2 imaginaries. They aren't right here, but again, the other 2 are imaginary. All right. All right, so let's first of all take a look at checkpoint number 1. You guys give it a shot. It should take you less than 10 seconds. All right, so the number of zeros, since this is third degree, this has 3 zeros. Now, are all 3 of those zeros guaranteed to be real zeros? Not necessarily. All right, that doesn't matter. All right, so now we're going to kind of take a look at this function here, and we want to look at of this polynomial function. Now, first of all, f of x is equal to x to the 5th minus 5x to the 4th minus 9x third, blah, 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 blah. All right? We skipped the lesson on rational zero theorem. All right? We didn't do the rational zero theorem, but basically the rational zeros would be any possible rational zero this thing might have is going to be the factors of 12 over the factors of 1. As I said, we skipped that lesson, and so what we want to do is we want to kind of take a look at our graphing calculator. Now, before we take a look at this function in the graphing calculator, what we have to recognize, first of all, is that this term right here is a typo. I need you to change that to plus 9x to the third. Otherwise, we're going to have a rough go at this. It's going to be pretty difficult, okay? But what I want to do then is I want to take a look at the graph of this thing. And so I'm going to slide over here. Again, please change that in your notebook. And what I want you to do is I want you to slide over to your graphing calculator, and I want you to input this function. Now, we plug in that function, and I want to go ahead and take a peek at that thing. All right, now, we know because of n behavior of this thing, since the leading coefficient is positive, all right, it is going to be odd degree, and as f of x goes to negative infinity, x is also going to negative infinity, and as x goes to positive infinity, f of x goes to positive infinity. So we know that my function, basically we're seeing pretty much all of it because my function is going to kind of have some of this kind of feel to it. So as I can see here, it looks like I have a solution right there, all right, and it looks like that solution is at -1. Well, how do we check that? Well, very easily, we go over here and we go to second, calculate, and I'm going to check a value at x equals -1. And when I plug in -1, cool, I get 0. All right? So that means that -1 is one of my zeros. All right? -1 is one of my zeros. Now, as we talked about from last section, we said that if x equals -1 is a solution, then x plus 1 is a factor. All right? And so what we want to do then is, like I said, we're just going to kind of get rid of all of this stuff. We're kind of doing this in the margin, so I apologize. We're going to end up doing some mess over here. All right? In recognizing then that we have a 0 at -1, we want to do a synthetic division because we know that the remainder, after dividing by the factor x plus 1 or doing a synthetic substitution of -1, we know that the remainder is going to be a 4th degree polynomial that we can continue to work on. All right, we'll come back to that in just a second here. All right, so this is 1, -5. Remember, this is +9, -5, -8, and 12. And we're going to go ahead and do our synthetic substitution. This is 1, -1, -6, +6, 15, -15, so this is -20, and so this becomes +20, which is +12. And lo and behold, this is -12, and so the last piece of this is gone. Now, after factoring out the factor x plus 1, or doing a synthetic substitution of -1, we are left with the function 1x to the 4th minus 6x to the 3rd plus 15x squared minus 20x plus 12. Now, I'm not going to rewrite that function because really that's kind of irrelevant to me. So don't write that stuff in there, because now what we're going to do is we're going to continue and go back and look at our graphing calculator again. To wipe that off, go back to our calculator. Now, are there any other values that it looks like that we have a 0? Well, it kind of looks like maybe we've got a 0 over here at 2. All right, and so if I go to second, calculate a value and say x equals 2, cool, y is equal to 0 there as well. Now, going back to the definition we just defined, we know that 2 is a double root. Okay, we know that 2 is a double root, meaning it touches there and then it goes away. So what that says to us is that because it's a double root, x minus 2 is a factor twice, because we have x minus 2 as a factor because 2 is a solution. And because it's a repeated solution, we know that we have that factor twice. What we're going to do then is we're going to factor out an x minus 2, or again, substitute in a 2. Again, do our synthetic substitution. 1 comes down. This is 2, -4, -8. This is 7. This is 14. This is -6, and -12, and 0. Cool. Once again, this is 1x to the 3rd minus 4x squared plus 7x minus 6. Don't care about that. Let's do it again. Let's plug in another 2 because, again, I have a double 0 there. This is 1, -2, -4, 3, and +6. And so that's all gone. So after factoring out an x plus 1, an x minus 2, twice, because x minus 2 was a factor twice because of the double zero there, we are now left with the rest of this thing, which is x squared minus 2x plus 1. All right? Okay. So here's the thing. This does not factor. Okay? We can monkey around with our need two numbers that multiply to 3 that add to negative 2. Unfortunately, that doesn't work. Okay? We can't come up with this as a factored version. And so, again, if we're taking a look at the zeros of this thing, going back to my graphing calculator, we can see that our graph has 3 real solutions, a double zero here and a single zero there. So there are 3 of the 5 solutions that we have to have. Notice right here it's 5th degree, so it has to have 5 solutions. So what does that mean that the other 2 are? Well, it means the other 2 are imaginary. Let's use our quadratic equation for the rest of this. X equals opposite b plus or minus the square root of b squared minus 4ac all over 2a. All right, now inside of the square root, we have negative 2 squared, which is 4, and then 4 minus, this is 4 times 1 times 3, which is 12. So this is going to become 4, take away 12 under the radical. In front, you still have the 2 plus or minus, and the whole thing is over. So it's 2 times a, and a is positive 1. Sorry, I don't know where I got the negative there. So this is now 2. Under the radical, now we have 4 minus 12, which is negative 8. And so the square root of negative 8 becomes 2i radical 2. Okay, because the square root of the negative becomes an I. The square root of 4 is 2, and that leaves a 2 underneath. All right, and so when I simplify this, this becomes then 2 plus or minus 2i radical 2 over 2. 2 goes in there once, and so this is 1 and 1. So as a result of all of that, then, we get that we have zeros at 1, a double root at 2, a double root at positive 2, all right, a double root at positive 2, and I'll put double down here. And that double root at positive 2 gives me 3 of my solutions. The other 2 are imaginary, and they are 1 plus I radical 2 and 1 minus I radical 2. All right, now I'm not sure that we're necessarily seeing yet the power of the fundamental theorem of algebra, but again, we knew that because this thing had to have 5 solutions, we could see right from the picture that 3 of them were real. So going back to the graph, 3 of them were real. We got a double zero at 2 and a single at negative 1. And so that meant that the other 2 had to be imaginary. So that means that when I did my quadratic formula and I got something down here that was imaginary, that's good news. I kind of knew ahead of time what I was looking for. That's what I'm looking for. 4th degree polynomial. And we have, looks like now we have a real solution at around negative 1 and one at 1, 2, 3, and 4. And so how do we check to see if those are solutions? Plug them in. Plug in negative 1. And it looks like negative 1 is a 0. So if negative 1 is a 0, that means that x plus 1 is a factor. All right? We can also see that x equals positive 1, 2, 3, 4. And so that means x minus 4 is a factor. How do we check that? Second, calculate a value when x equals positive 4. I get a 0 as well. So it looks like, according to the calculator, I get 2 real zeros, and they are at negative 1 and positive 4. I'm sorry, positive, yes. X plus 1 and x minus 4. So my zeros are at x equals negative 1 and x equals positive 4. So how do I use synthetic substitution to figure out what's the resulting quadratic? Now, let's think about this. We have 2 real solutions, so the other 2 must be what? That's right, imaginary. 1, negative 7, positive 13, 1, and negative 20. We're going to plug in a negative 1 here, because that's one of my zeros. This is 1, negative 1. That becomes negative 8. Positive 8, so that becomes 21. This is negative 21, which is negative 20. And that's positive 20, which is 0. Cool. Okay. We knew that we're going to get a remainder of 0 because negative 1 is one of the zeros. Let's try 4 now. Plug a 4 into the resulting polynomial. Again, this is now a 3rd degree polynomial. X to the 3rd, x squared, x to the 1st, and no x's, right? So let's do this again. This is 1. That means this is 4. This is negative 4, negative 16, 5, and 20. Cool. 1x squared minus 4x plus 5 is the resulting polynomial after factoring out an x plus 1 and an x minus 4. So those are those two factors. The rest of this we know does not factor, and why do I know it doesn't factor? Because if I go back and look at the picture of the graph of this thing, it only has two real solutions that I can see. So the other two are actually imaginary solutions, and they're going to come as a result of solving this using the quadratic formula. X equals opposite b plus or minus the square root of b squared minus 4ac all over 2a. Now, this is 4 plus or minus. Square root of 4 squared is 16, and 16 minus 20 becomes negative 4. So I have square root negative 4 all over 2. All right, now the square root of negative 4 is the same thing as 2i. So this is 4 plus or minus 2i all over 2. And if I reduce everything by a 2, this becomes 2 plus or minus i. So my solutions are x equals 2 plus I, 2 minus I, negative 1, and positive 4. How many zeros do I have to have? I have to have 4 because of the fundamental theorem of algebra. All right, complex conjugates theorem. Complex conjugates theorem is kind of a big deal too. The complex conjugates theorem and the irrational conjugates theorem really amount to the same thing, and that is that complex and imaginary solutions come in pairs. All right? So it says if f of x is a polynomial function with real coefficients, and a plus bi is one of the imaginary zeros, then a minus bi is also an imaginary zero. Suppose f is a polynomial function with real coefficients, and a and b are rational numbers such that the square root of b is irrational. All right? If a plus radical b is a solution, then a minus radical b is also a solution. All right, so let's see how that shakes out for us on the next page here. So we're going to talk about building a polynomial function now. Okay? It says use zeros to write a polynomial function. Write a polynomial function of at least degree of the least degree possible that has a real coefficients, a leading coefficient of 1, so that means that the first term is 1x to the something. All right? And it has negative 2 and 3 plus I as zeros. So we want the least degree that's possible with that. So that means that x plus 2 is a factor, right? And we also know that since 3 plus I is a 0, then 3 minus I is also a 0. All right? Now, just like before when we said if x equals negative 2 is a solution, then x plus 2 is a factor, all right? Basically, it's just x minus the 0. In this case, since it's negative 2, it becomes x plus 2. So we're going to do x minus the 0, and one of the zeros is 3 plus I. That's given. And the other one has to be 3 minus I. All right? That has to be 3 minus I because if one of them is a 0, then the other one has to be as well. All right? So our next order of business then is we're going to go ahead and take a look at expanding this product. Now, I'm not going to worry about it. I'm just going to take my subtract and make it plus the opposite and the opposite, plus the opposite and the opposite. Now, x and negative 3 and I, none of them go together. One's a variable, one's an I, one's an x. So I'm going to use my idea of Punnett squares. I'm going to go ahead and multiply these out. Now let's just fill out our squares. X times x, x squared. X times negative 3, negative 3x. X times negative I is negative xi, or I could do ix, it doesn't matter. X times negative 3 is negative 3x. Negative 3 times negative 3 is positive 9. Negative 3 times negative 1 is positive 3i. X times I is positive xi. I times negative 3 is negative 3i. I times negative I is negative I squared. All right, now we got a bunch of stuff that's going to clean up here. What's x, negative xi and positive xi? That's right, they cancel. Positive 3i, negative 3i. That's right, they cancel. Combine like terms, this is now x squared minus 6x. And then I have plus 9, and then on the end I have negative I squared. Well, remember, negative I squared is the same thing as negative 1, right? So it's negative of negative 1, which becomes positive 1. All right? And so this whole polynomial, as a result of foiling those two, becomes x plus 2 times this mess, which is x squared minus 6x plus 10. All right, now I'm running out of paper here, so I'm going to go over to the other side. Now I have to multiply a binomial times a trinomial, and this is just Punnett squares again. This is x plus 2, this is x squared minus 6x and plus 10. This is x to the third, 2x to the second, this is negative 6x squared, this is negative 12x, this is 10x, and this is 20. Now, as a result of foiling that, this becomes x to the third minus 4x squared minus 2x plus 20. And that polynomial with the leading coefficient of 1 has 3 solutions. One of them is 3 plus I, one of them is 3 minus I, and the other one is negative 2. All right? Try the checkpoint problem down below. We will be back with a solution for that tomorrow. Unfortunately, I'm running out of time here today to finish recording. We are not going to be doing the Descartes rule of signs, so I want you to try this checkpoint problem, and we'll be back, and that's the first thing we'll discuss tomorrow when we go over that solution.